Unit 2 Chemistry, Chapter 18, Part 3. Another way we can analyse salts in water is using a process called spectroscopy. And we're going to look at two different types of spectroscopy. One which is called atomic absorption spectroscopy, or AAS, and another one which is called UV visible spectroscopy, or UV-vis for short. So AAS, first of all, this is based on the same principles as flame tests. So if we remember, when excited valence electrons of metal ions fall back towards ground state, they give out light. Okay, and you can use that wavelength of light that's given out to identify the element. But when they go from ground state to the excited state, they absorb light. And they're actually going to absorb exactly the same energy that they emit when they go back in the other direction. Okay, because remember, energy can't be created or destroyed. So essentially what we're doing is we're changing it from light energy to chemical energy. And then when it's given out again, it goes from chemical energy back to light energy. What we're going to look at in atomic absorption spectroscopy is the energy that is absorbed, because that's more accurate and we can use it for a wide range of elements. So essentially what we do is we take a white light source and we shine it through a sample which is a gas. That is going to go through a slit just to get one narrow beam of light, and then through a prism which is going to split it up into a rainbow essentially, but we're going to get just distinct bars, and we're going to use that and that will give us our absorption spectrum. So an absorption spectrum looks essentially like the negative of the emission spectrum. Okay, this is obviously a rainbow, but here, these black lines, they're the wavelengths of light that are absorbed. And this one is unique for hydrogen, and this one here, that's unique for sodium. So here, this is the absorption spectrum. Down below, that's the emission spectrum. So you can see they're the reverse of each other. Now, the way we normally use it is to find the concentration of the metal, okay, because this is used for metal things. So you choose just one wavelength. So for hydrogen we might choose this one. For sodium we might just choose that one there. Okay, but you select one. And it's got to be a wavelength that the metal absorbs. The basic principle is the bigger the concentration of the metal, the more light will be absorbed. Okay, so we start by making a whole set of standards. And the standards are things where we know it's their concentration. And we put them into our AAS machine. And using that, we find how much light is absorbed by these standards of different concentration. And we use that to make a graph that we call a calibration curve. Okay? Your graph is going to look like this. So these are the concentrations that we know, and this is how much light of one particular wavelength was absorbed. Okay? We then have our unknown that we don't know the concentration of, but we know it's got the same metal in it. We put that in and we measure its absorption. And then from our graph, we read off our absorption, say it was 0.4, and we read down to this axis and we find its concentration. Okay, so this is kind of how it looks. We give out the light, we vaporize it, turn it into a gas. Okay, we go through a prism to split it up into the different wavelengths of light, and then we use this slit to just choose one of those wavelengths. And this detector measures just how much light is absorbed by each of the standards, and then just how much light is absorbed when we do the final one with our unknown substance. We can use it, as we say, to find metals. So you might use it to look at, say, the iron content in blood. Okay, lots of people, particularly women, end up anemic. So we might look at it to see, well, is there enough iron in their blood? We can also look at toxic metals in drinking food, so things like mercury in fish, to see if it's got safe levels to eat. We can look at pollution in air and soil, and engine oils, because that might cause engine failure if there's too much in there.